Hello everyone, my name is Sima Neyrizi. I'm a student at ITS University in Geomatics Engineering, and now I'm going to present my research with the topic of nitrogen dioxide mapping of Perth bushfire utilizing Sentinel-5P TROPOMI. My presentation is including introduction, methodology, results and analysis, also closing. As we all know, all over the world, including Australia, grappling with diverse environmental challenges, including bushfire. The bushfire that happened in Australia is a world bushfire that happened on 1st of February 2021, and it continued till 6th of February 2021, and it burned the area around 11,000 hectares. From this fire, air pollution enters to the atmosphere, including nitrogen dioxide, which this pollutant cause severe health problems and negatively impact plant growth. For monitoring this pollutant, the Sentinel-5P satellite imagery can be utilized for monitoring the concentration of nitrogen dioxide before, during, and after the rural bushfire. Also, to be able to compare these values with ground station values that comes in microgram per cubic meter, the unit conversion method employed for this research. The question of my research are how to extract nitrogen dioxide value in microgram per cubic meter from Sentinel-5P, employing the conversion method. Also, how does the conversion of satellite data from mole per square meter to near ground data, meaning microgram per cubic meter, affects the accuracy of pollutant estimation? What is the spatiotemporal distribution of nitrogen dioxide in Perth City before, during, and after the fire? Also, how do environmental parameters such as land surface temperature, precipitation, wind speed, and wind direction influence the spatial and temporal variation of nitrogen dioxide concentration? The study area is Greater Perth, and the data that are utilized, including Sentinel-5P satellite imagery. There are 5 reanalysis dataset, including land surface temperature, precipitation, wind direction, and wind speed, administrative boundary of Greater Perth, burned area boundary. The method that was utilized is unit conversion method that changed the unit from mole to mole per square meter to microgram per cubic meter. And for the result, the accuracy test was utilized, including R-square, NMAE, and RMSE. Also, the results analyzed with the additional data from January 2021 to February 2021. The objective of the research was to do unit conversion method, that changed the units from mole per square meter to microgram per cubic meter. And then from the result, the create the model to apply in whole area. Also, for the results of both unit conversion and model creation, the accuracy evaluation was done, and the analysis was done utilizing LST, wind direction, wind speed, and precipitation to check the effects of these parameters on nitrogen dioxide distribution and values. The study area is Greater Perth, including Perth City, Mandurah City, and Pinjarra City. As it can be seen in the map, the white area is Greater Perth. There are 8 ground stations, 6 for validation with the color of blue, and 2 reference station, which was utilized for creating the model with the name of rolling green and cover sham with the color of green. And the red area is the burn area. The starting point of the fire is orange area. As I already mentioned, the data that was utilized are including Sentinel-5P satellite imagery, the tropospheric band, and administrative boundary of Greater Perth with the format of shapefile, burned area boundary with the format of shapefile, ground level nitrogen dioxide data, including 8 stations that I already mentioned, 6 for validation and 2 for creating model. Land surface temperature, precipitation, wind direction, and wind speed from ERA 5 reanalysis dataset. As I already mentioned, 2 ground stations that are close to the burned area, namely Coversham and Rolling Green, with the distance from the fire area 13 kilometer and 7 kilometer respectively, were employed for creating the model, and other 6 remaining stations were utilized for the validation. The unit conversion method is shown in here. In fact, it interpolates the ground and satellite data with dividing the maximum value of the ground to a maximum value of the satellite imagery and multiplying it to the satellite imagery. And in fact, it is showing that how many times the ground data are bigger than the satellite imagery. The processing is, as can be seen in the flow chart. First, the maximum value of the burned area and also the maximum value of both reference ground station, namely Rolling Green and Coversham, extracted, and then conversion factor obtained from dividing the maximum value of nitrogen dioxide to from the ground to maximum value of the nitrogen dioxide from the imagery, and then it applied to the image itself to gain the value to obtain the value of Rolling Green and Coversham in microgram per cubic meter. Then in fact, the near ground estimated value of nitrogen dioxide at Rolling Green and Coversham was obtained. And then to check how unit conversion affects the accuracy of the results, the correlation coefficient RMSE and NMAE between the ground value of both stations with both satellite drive and converted data calculated to see how it affects. And after seeing how does the unit conversion affects the accuracy, the regression analysis was done between the converted data or estimated data with the satellite with ground station data. And from that, several algorithm can be obtained, which the one that has the highest R square and lowest RMS error was chosen as the best algorithm. And then it was applied to the whole Perth area. Then the predicted nitrogen dioxide in microgram per cubic meter was obtained, and then the RMSE and NMAE calculated for each of 6 validation ground station was calculated, and then from to see if it how is the accuracy after applying the model and before applying the model, and then from the predicted nitrogen dioxide, the distribution map of nitrogen dioxide in Perth area pre, during, and after the fire created, and this distribution maps and data analyzed with additional data, including land surface temperature, precipitation, wind direction, and wind speed. Results and analysis. With the change in the unit of nitrogen dioxide derived from Sentinel-5P, 2 microgram per cubic meter, the accuracy improved significantly. The correlation coefficient increased from 0.5 to 0.8 after conversion, indicating a stronger relationship with the measured values. The RMSE decreased from 7.5 to 3.2, showing a reduction in the average error. Additionally, the NMAE decreased from 1 to 0.4, suggesting an overall improvement in the accuracy of the estimated nitrogen dioxide values. A regression analysis was conducted to establish a model linking satellite-derived nitrogen dioxide data converted to microgram per cubic meter with ground-based nitrogen dioxide measurements from 2 reference monitoring stations, Rolling Green and Coversham. From several, as I already mentioned, from several fitted curves, the linear regression model showed the highest R square around 0.7 and the lowest RMSE 2.7 microgram per cubic meter. This suggests that the linear model is the most suitable approach for predicting nitrogen dioxide concentration in microgram per cubic meter across the entire study area. The model applied to the images pre-fire, during, and post-fire, and then predicted the nitrogen dioxide values from the model were compared against ground truth data from 6 additional monitoring stations. Figures illustrate the comparison between the predicted and ground truth nitrogen dioxide data for each of 6 validation stations. Additionally, the statistical measurements for each station are presented in table. The comparison results indicate varying degree of accuracy across different stations, reflecting both the performance of the model and the inherent variability in the satellite data. This variability reveals different behaviors at each station, which influences the accuracy and effectiveness of the model. Distances from the fire, as it can be seen in the table, didn't consistently correlate with the model performance. For example, stations closer to the fire, like Dunkirk and Queen's Rock, showed lower RMSEs compared to the more distant Rockingham. Mandurah, despite being farther away, had the best performance, suggesting local factors like topography and meteorological condition significantly influence nitrogen dioxide distribution. As we can see in the second table, the analysis showed improved nitrogen dioxide predictions with satellite-derived RMSE and NMAE values generally higher across all stations. For instance, Dunkirk's RMSE improved from 8.46 microgram per cubic meter, which is satellite-derived, to 5.26 microgram per cubic meter. It is derived from model. In summary, while Mandurah had the highest precision, overall model performance is shaped by local topography, meteorological conditions, satellite data resolution, and difference between TROPOMI and ground station measurements. After validating the model and applying it to images, a comprehensive spatiotemporal analysis was conducted for greater pairs, focusing on mean and maximum nitrogen dioxide values over 3 periods: 7 days before the fire, 6 days during the fire, and 7 days after the fire. From mean nitrogen dioxide data, it can be seen that before the fire, mean nitrogen dioxide ranged from 2.6 to 4.7 microgram per cubic meter. During the fire, mean nitrogen dioxide increased to 5.7 microgram per cubic meter, and after the fire, mean nitrogen dioxide decreased to pre-fire levels between 2.6 and 4.4 microgram per cubic meter. Considering the maximum nitrogen dioxide values before the fire, it ranged between 3.8 and 11.5 microgram per cubic meter. The highest peak on 31 of January reached 11.6 microgram per cubic meter. During the fire, it peaked at 27.7 microgram per cubic meter on 1st of February, surpassing the World Health Organization's 24-hour air quality guidelines level of 25 microgram per cubic meter, as it can be seen in the table. And after the fire, maximum values remained elevated between 3.8 and 11.7 microgram per cubic meter. Spatiotemporal maps reveal that before and after the fire, nitrogen dioxide was concentrated in the western urban regions of Greater Perth. During the fire, high nitrogen dioxide values shifted to the northeastern part, reflecting the bushfire's impact. Mean nitrogen dioxide value generally met whose standards, while maximum values indicated short-term exposure risks exceeding whose 24-hour air quality guidelines level during the fire. The fire caused severe air quality deterioration with substantial health risks highlighted by peak nitrogen dioxide levels. Post-fire, nitrogen dioxide concentration gradually returned to normal, indicating the transient nature of bushfire-related pollution spikes. The analysis underscores the significant impact of the Wooroloo bushfire on nitrogen dioxide level in Greater Perth and the need for targeted air quality measures during such events. It is important to highlight that air quality is influenced not only by pollutant concentrations such as those from bushfire, but also by local and regional climatological and meteorological conditions. Therefore, these factors and parameters should be analyzed to understand their influence on atmospheric nitrogen dioxide levels. This study investigated the influence of LST, precipitation, wind direction, and wind speed on nitrogen dioxide concentration. According to the first table, nitrogen dioxide levels increased significantly during the fire from 3.7 pre-fire to 0.42 microgram per cubic meter during the fire. This rise suggests a direct influence of the fire on nitrogen dioxide emission, likely from combustion processes. Post-fire levels decreased to 3.8 microgram per cubic meter, but remained higher than pre-fire levels. A marked decrease in LST was observed during the fire period, with pre-fire values at 36.5 degrees Celsius, dropping to 33 degrees Celsius during the fire and further down to 27 degrees Celsius post-fire. This significant pre-fire LST likely contributed to dry condition, creating an environment conducive to fire ignition and the spread. During the fire, the decrease in LST might be attributed to factors like firefighting efforts like water spraying and rainfall, which could lower surface temperatures. Post-fire cooling might be due to both fire containment and continued precipitation. The observed changes in LSD and nitrogen dioxide levels suggest a potential connection. High pre-fire LSD might have created drier conditions that facilitated the fire and the subsequent increase in nitrogen dioxide emissions from combustion. The precipitation increased during and after the fire compared to the pre-fire period. Although the increase is relatively small in absolute terms, it indicates more moisture in the atmosphere. The extremely low precipitation pre-fire likely contributed to the dry condition that facilitated fire ignition and spread. Higher precipitation during the fire may have helped to decrease LSD by introducing moisture into the atmosphere and the surface. Increased precipitation during and after the fire can also aid in the removal of nitrogen dioxide from the atmosphere through wet deposition, which might explain the reduction in nitrogen dioxide levels post-fire. The relationship between nitrogen dioxide and key environmental factors, LSD, wind speed, and precipitation, were investigated. Considering the correlation analysis, the weak positive correlation between nitrogen dioxide and LSD around 0.2 suggests a modest association between higher temperatures and increased nitrogen dioxide levels. High LSD can indicate extreme heat conditions, which are conducive to fire occurrence. Elevated temperatures can enhance the formation of nitrogen dioxide through increased combustion rates and photochemical reactions. Thus, higher LSD might lead to more frequent or intense fires, which in turn increases nitrogen dioxide emissions. Although the correlation is not very strong, it highlights the role of temperature in influencing nitrogen dioxide levels indirectly through fire events. The strong positive correlation between nitrogen dioxide and wind speed around 0.8 indicates that higher wind speeds are significantly associated with increased nitrogen dioxide levels. High wind speeds can lead to the spread of fire, making it larger and more intense, which in turn generates higher nitrogen dioxide emissions. Increased wind speeds during the fire likely facilitated both the growth of the fire and dispersion of nitrogen dioxide over a larger area, resulting in elevated concentration. The weak positive correlation between nitrogen dioxide and precipitation around 0.2 suggests that precipitation has a limited impact on nitrogen dioxide levels. While rainfall can help remove nitrogen dioxide from the atmosphere through wet deposition, it might also trap nitrogen dioxide and other pollutants close to the ground. During periods of high precipitation, the atmosphere may become more humid, potentially leading to temporary trapping of nitrogen dioxide rather than its removal. This can create a complex interplay where increased precipitation might contribute to higher observed nitrogen dioxide levels in the short term. Although overall, it still plays a role in cleansing the atmosphere over time. LSD and precipitation distribution maps are shown in here. The LSD maps revealed interesting patterns associated with the fire event. Before the fire, the mean land surface temperature was relatively high, reaching up to 44 degrees Celsius. This elevated temperature could be one of the contributing factors to the fire's ignition, as higher temperatures can increase the likelihood of combustion. During the fire, the LSD decreased, and after the fire, the LSD stabilized around 23 degrees Celsius, indicating a return to more typical temperature condition for the area. The precipitation maps further contextualize the environmental conditions surrounding the fire. Before the fire, there was virtually no rainfall, which combined with high LSD likely contributed to the fire's ignition. During the fire, precipitation levels increased, reaching up to 0.04 millimeter. This increase in rainfall could have helped in reducing the LST. The analysis of wind direction and the speed reveals a complex interaction with nitrogen dioxide distribution. During the Whirl Bushfire event, the prevailing wind directions before and after the fire were primarily from the southwest, contributing to the observed nitrogen dioxide distribution patterns. During the fire, easterly winds transported nitrogen dioxide towards the west, significantly increasing concentration in the northeastern part of the study area. Elevated wind speeds during the fire facilitated the spread of the fire and dispersion of nitrogen dioxide, while high post-fire wind speeds aided in the reduction of nitrogen dioxide levels as the fire was contained. These findings highlight the critical role of wind in influencing air quality during bushfire events. The spatial and temporal variation in wind direction and the speed underscores the need for continuous monitoring and analysis to understand and mitigate the impacts of such natural disasters on air quality. The conclusion of my research is as following. This study used a unit conversion method to transform Sentinel-5P satellite nitrogen dioxide data into near ground concentration in microgram per cubic meter, improving environmental assessment accuracy. The conversion increased the correlation coefficient from 0.5 to 0.8 and reduced RMSE from 7.5 to 3.2 and NMAE from 1 to 0.4. Regression analysis was done between the converted and measured nitrogen dioxide for the two reference ground stations, and the linear regression showed the highest R square around 0.67 and lowest RMSE 2.77 microgram per cubic meter, making it superior for predicting nitrogen dioxide, and then it applied to all area. And validation with 6 additional stations showed varying accuracy due to local factors like climatological parameters and the elevation and other parameters. Mandura station had the lowest RMSE around 2.4 microgram per cubic meter, indicating high precision, while other stations had higher RMSE values due to environmental variation. The spatiotemporal analysis showed significant nitrogen dioxide changes due to the Whirl Bushfire. Nitrogen dioxide peaked at 27.7 microgram per cubic meter on 1st of February 2021, exceeding whose 24-hour air quality guidelines level. Post-fire nitrogen dioxide level decreased but remained higher than pre-fire level, indicating the fire effects, and also analysis of land surface temperature, precipitation, wind direction, and wind speed revealed their impact on nitrogen dioxide concentration. During the fire, nitrogen dioxide level rose with a 2.5 degrees Celsius decreases in land surface temperature and a 15 millimeter increase in precipitation. The wind direction shifted northeast and speeds increased from 3.2 meter per second to 5.6 meter per second, influencing nitrogen dioxide distribution. These factors highlight the need to consider multiple environmental parameters in air quality assessment during and after the fire. The suggestions from this research can be like following. Exploring satellite dataset with higher spatial resolution than Sentinel-5P could provide more detailed insights, and employing advanced machine learning models can help for more accurate prediction of pollutant. More in-depth analysis can be performed to understand the distribution and behaviors of nitrogen dioxide and other pollutants with different land cover types, and utilizing satellite platforms with higher temporal resolution could allow for more frequent monitoring and dynamic assessment of air quality changes during wildfire events, as the Sentinel-5P temporal resolution is daily, and integration of ground-based measurements from locations with burn areas could enhance validation and calibration processes. As for my study, the two reference ground stations were not located exactly in the fire area. One of them with the 7 kilometer distance and another 13 kilometer distance. So if we choose the one the most close, more close than this station, maybe it affects the accuracy. These are the references that I have utilized for my presentation. And this is the end of my presentation. Thank you so much for your time and attention.